In section 8.2, we constructed a confidence interval to estimate a population proportion. This time we're going to do the same thing, but for a population mean. So again, it has this form of the point estimate. Prior, for the proportion, we used the point estimate to be p hat. Now we're doing it for mean, so we'll use x bar, plus the margin of error. And the margin of error is typically for a 95% confidence interval, so we use 1.96 standard deviations times the standard error. We're going to basically do the same thing here. The thing that will change will be the standard error. Prior, for proportions, the standard error was defined to be standard deviation for the sample proportions distribution, and that was p hat times 1 minus p hat divided by n, and then you take the square root of the whole thing. For the sample mean, it becomes sigma over square root of n. And since we don't know sigma or mu for the original population, we estimate it by putting in S, the standard deviation for the sample. And we're going to divide that by the square root of n to get the standard error. I don't know why they use that name, but they do. So instead of having p hat plus or minus z, and z is usually 1.96 times the square root of p hat times 1 minus p over n, we now have x bar plus or minus z times sigma, which we're going to substitute with by s over the square root of n. Now when we do that substitution using s, we get a little extra error. Now, to account for that, we're actually going to use a t-score many times. So the confidence interval becomes a little bit wider, but it works pretty well. So it still looks like the standard normal curve we're looking at, but if we actually were able to measure it, the tails would be a little thicker, and we'll use something called the degrees of freedom. And to do that, we basically take the value n and subtract 1 from it. So it's pretty easy to do. And if that became a really huge number, degrees of freedom became really huge, it then actually becomes normal distribution. So it's also symmetric about 0, just as the normal shape, the normal distribution was, normal curve. And we're going to take the t-score instead of the z-score this time and multiply it by the 1.96. And you'll see here they actually have several of these curves drawn, because when you do t-distributions, depending on the degrees of freedom, you get a slightly different curve each time. You see the lowest one there has the degree of freedom of 3, and when it is a degree of freedom of 6, it's higher. And the ideal that you get to would be the normal distribution is the tallest one of the 3. So on the left you'll see degrees of freedom, which you'll go to find. Then you'll look for your confidence level. So for the one for 6, we would go to degrees of freedom 6, which means n equals 7. We come across, come underneath where we want a 95% confidence interval, and we find the t-score of 2.447. That's what we'd be multiplying by 1.96. Now note down here at the bottom, it says when n equals 7, degree of freedom equals 6. And t sub 0.025 equals this. Now why are we using that if we're doing a 95% confidence interval? Well, 0.025 is 2.5%, and this is a two-tailed probability, so we take 2.5% and multiply by 2, we have 5%. That's the part we're excluding, so we're looking at the 95% in between those values. So it all works out. Here they show you a picture representation of it. And so they might show you something like z and then have a alpha over 2. That's the same idea. And here it would be t and then have a subscript of alpha over 2. Alpha being the 0.05 or 5%. And here you see it in practice, x bar plus t, subscripted with a 0 to 5, standard deviation of the sample over the square root of n, and definition of what degree of freedom is. So go through an example here. This is in your book as well, I believe. You notice there's 11 completed auctions. That means n equals 11. degree of freedom equal 10. So now here's a graphical display to check the assumptions. Does this look like it might be a normal distribution? Well, it kind of seems to be centered around 580 or maybe 590. So that looks fairly reasonable. And if you see the box plot at the bottom, you see a line there. That line is the median, I believe. So that's a measure of center. So it seems to be centered around 590 if we're using median. We find the standard error by taking S over the square root of n. S was equal to 22.15, square root of 11, and we get 6.68. We plug it in, multiply instead of times to 1.96, 2.228, which is what we found by looking in the t-table. And we came up with a number to add and the same number to subtract from 583.64, which was x bar. You notice here they use parentheses 568.8, comma 598.5, parentheses for an interval notation. And no one really uses 99% confidence interval. By robust, that means it stands up to where when you kind of violate some of the conditions. As long as you don't violate them too badly, you can still use these things. And here they talk about the normal distribution is the t-distribution with the degrees of freedom equal infinity. And that ends this section.